Good afternoon. This is the first time I happen to participate in this Congress, Enoforum, and I would like to thank Agrovin for giving me the opportunity to take part in this very interesting event. I'd like to start by discussing ionic exchange of the many types of materials that can be used for this purpose, and we'll also be discussing about some theoretical aspects, although to a limited extent, with respect to the properties that these materials have to have. We'll also discuss some applications that we have studied and investigated when it comes to the use of these materials, particularly for oxidized white wines. First of all, let me discuss some ionic exchange resins. Nowadays, they look like this, and they contain these small particles. The process in itself is such that a solid will take ions from a fluid, and in exchange for that, it will provide to it an equal quantity of ions with the same charge. The ions which are taken and given needs to respect the principle of charges. The same number of charges yielded by the resin must be the same as what is absorbed by the fluid. There must be balance. The resins can be positive ion exchange resins, such as in the case on the left-hand side. There's an exchange of sodium and calcium ion exchange. Or, as we shall see later, there might be anionic exchange resins. This is what I was announcing. In the former case, it's the sodium ions of the exchange resin that will go into the fluid, and in exchange for that, the fluid must have the resin retain some positively charged ions in the same numbers as the ions exchanged. So in the anionic in exchange, the electric charge is different. It's the same principle but with a different sign. Is it a modern technique or something recent by any means? Well, the answer is no. For instance, there are excerpts from the Old Testament, such as in the Book of Moses, where it is said that it is possible to purify water for it to be of drinkable quality by passing it through a relatively rotten piece of wood. And the explanation is not provided in the Old Testament. They didn't know what was going on. But we can imagine that it was an ionic exchange produced by the cellulose degraded and generated through the rotting process. And even before Christ, Aristotle, in his book Problemata, described that seawater can lose its saline concentration when percolated through sand. The sand on a beach, and more recently we can consider that this technique has been used more consistently after Thomson and Way gave their interpretation of the ionic exchange in farmland around 1850, when you have clay or silt containing soils. There's an ion exchange with the plant in order to provide the plant with the necessary ions so that it lives and develops in a satisfactory way. What are the materials that make ionic exchange with the surrounding fluid possible? What are these resins made of, or these materials at any rate? There are natural materials such as zeolites or other forms of or other types of clay, such as aluminum silicates that contain various ions such as iron or magnesium and so forth. But the humus in the soil can do the same. In the applications of Thomson and whey, that was the case. On top of that, a number of synthetic resins and synthetic materials were developed in the course of time. We're talking about synthetic materials because zeolites, in principle, can be produced naturally. You can have some 40 different types of zeolites. However, nowadays, also synthetic zeolites can be developed for the purpose of ion exchange, and so processed for technical, to serve technical purposes. So it can be a natural inorganic material. Now, what we call synthetic materials are basically the ion exchange resins. The ion exchange resins require a structural basic element, a polymer. It could be polystyrene or a divinyl benzene, a metacrylate, a polyesterane, and other combinations which will create a matrix on top of which you need to position the ion exchange sites, because the matrix in itself does not have the possibility to exchange ions. It is electrically neutral and has no separate charges. So these resins can be of different natures. They can be, first of all, classified based on their physical characteristics, whether they are porous or gel-like. The porous resins are those that contain hollows that are large enough to house this function and these exchange points, so as to allow the penetration in the exchange ions. With these resins, you can have well-defined sizes of the holes. You also have gel-like resins that are more limited because the hollows that are formed are not very large, so their use is more limited. In terms of zeolites, zeolites can have this appearance once they're processed. These are granular materials, others that are more powdery, and others still where you can tell the various particles with a naked eye. You have a crystalline structure at the basis of any zeolite, and then a basic crystalline material called sodalite, and that's where the silica and aluminum atoms are. These basic units, these structural units, are repeated with different morphologies throughout the entire range of zeolites. You can have a structure like this, as you can see here. It's a structure that contains relatively small pores inside this structure, but when they combine together, larger pores are formed. If you control the positively charged ions that accompany this aluminum silicate, it is possible to design new structures with hollows of different sizes. Therefore, it is possible to create synthetic zeolites, which are currently as numerous as approximately 150 on top of the 14 natural zeolites, thus covering the entire range of possible applications. When you have synthetic resins, you need to create a 3D matrix structure to support these ionic exchange points. One of the materials used for this purpose is polystyrene, a well-known material which is used in its expanded form and very often in packagings. We all know this material. In Spain, by the way, it's called white cork. Another material which is pretty often used and that makes it possible to create larger hollows, larger holes, and more rigid structures are copolymers that contain polystyrene and divinyl benzene. As we shall see, this opens up to many possibilities. But what characterizes these ion exchange resins? Well, we could discuss this on end There are several theoretical factors that come into play. Ion exchange is dealt with on a par with adsorption, and there are many aspects that I should discuss, but that I won't, because this is not the purpose of the presentation. But what matters here is that there are some practical aspects in these applications which are relevant to our subject here for our standard applications. We're interested in knowing what's the distribution of the size of the particles, and that will be explained by this artwork. It could be the average diameter of the particles. Here you have different diameters. It can be the most frequent particle diameter, particle size diameter, or the range between the smallest and the largest, which is what we call mesh. So a characteristic of a resin is always defined according to this criterion. Another element is the specific superficial area, which is the area where the exchange takes place. These are the hollows inside the particles. They create these balls of synthetic. They are balls of synthetic material with the holes in between. The functional groups need to be well placed so that they can effectively perform the ion exchange. Now, these spaces are very important, and their diameter matters a lot, and it is the total area that they develop that matters, and it depends on the size of each opening and the diameter of each of these ramifications among the particles. We also need to know well how much space there is between and among particles, because it is these spaces that dictate another relevant characteristic, which is the resin density. It can be the density of individual resin particles per se, or the density of the bulk product as part of a lot of production. The distribution of the particles plays a very important role. And if the particles are very different or very similar among them, the spaces can accordingly be smaller or larger. These interspaces also play a key function, which is to make it possible to work with a continuous flow, because it is possible to remove ions from a solution, adding resin and then filtering, or by placing resin in a big column or in a large tube or piping, where you keep it in a fixed stage and then a flow is circulated through the resin. In that way, these interspaces will play a very important role in the application of the necessary pressure to get the fluid through this system.
Distribución de tamaño de poro.
We then have the porosity or distribution of pores in function of size. We have large ones, such as that one, or intermediate size pores, or very small pores. Micropores are those where you can have ion exchange, and specifically the one we are interested in. If the pore is too large, then the ion we are interested in and we want to capture, it can go through the canal and does not interact with the functional group. A similar phenomenon happens with mesopores, medium-sized pores. There you have more possibilities of interaction, but it is at micropores, in micropores, that you have contact between the functional groups and dissolved ions. So the functional groups will remove the ions. The resins, what about the resins, that we can find on the market? Well, they are classified differently. For instance, in function of the type of polymerization reaction or the conditions in which polymerization occurs in order to create the synthetic matrix of the resins. For instance, we might have gel-like resins, and one very common case is that they are polystyrene resins with a small quantity or percentage of vinyl benzene in order to favor cross-linking. What you have is microporosity, again depending on the size of the molecule. It is the natural porosity that can be generated by the coming together of these two structural elements which are part of a resin. We can increase the size of the cavity and the specific internal surface, because what we're interested in this case is taking away the smaller and larger volume ion. One sodium or calcium ion, well, they are two different things. Their size is different, and macro-reticulated resins can be used for that purpose. In that case, you increase the percentage of cross-linked material, for instance, polystyrene, with a higher quantity of vinyl benzene, and you use a mixture during the formation of the copolymer, and it is a porogenous substance, that is, those substances that do not participate in the copolymerization reaction and that prevent the formation of polymers in the place they take, but then they can be easily removed. We saw that with a number of solvents. In that, you have the product go through that, or you can eliminate easily, which means that you're left with a bigger cavity and in that case, increasing the size of the cavity and increasing the links and bonds entail a higher internal volume, which is an advantage, and you also have fewer differences in the swelling of the resin, because when it gets impregnated with liquids, it integrates them, and you see a high polarity liquid with water or another liquid such as ethyl acetate produce two different reactions. In a number of cases, a resin increases its volume to a larger or lesser extent. We can observe that resin put into a pipe through which we have a solvent pass through can increase and diminish in volume in function of the solvent. The micro-reticulated resins prevent these volume differences having an impact on the volume of the resin. When you change the solvent, these resins are subject to less reduction when drying and when being dried, and they also better resist oxidation, which means that they last longer and they can be used repeatedly. There is one example which is sort of extreme, which could be that of a Ethylosorb or a hyperpolystyrene and cross-linked, where we use higher percentages of benzene. 40% approximately of the resin or more is cross-linked. These are very rigid structures in mechanical terms. They better support this change in volume when the solvent is changed, some more than others, and their loading capacity is also higher, meaning that we can have bigger quantities of liquid go through the resin. It is usual to use polystyrene and divinyl benzene. Here we see the structure. Here we have divinyl benzene in red and styrene in black. Divinyl benzene has these two vinylic groups and they perform a role for reticulation. This styrene portion is where we place functional groups that see to the exchange of ions. The point is, if I mix these two components of resin, what do I obtain? I obtain a resin that in the beginning does not have these ion exchange locus. And then there is functionalization, which is a phase where these active loci, these points, are added and they are either negatively or positively charged. If we, for instance, take one part of the resin where we have a styrene group, it is easy to treat it with acid and introduce a sulfonic group with a negative charge. In that case, we will generate an exchange resin, which is a cation one, because the sulfonic group is negatively charged and a counter ion with a positive ion will be there and will be possibly carrying out the exchange. We also need resins that do the opposite, that say they exchange anions, and in this case we do not have a very direct function, not as direct as list. In this case, we use a reactive agent, which together with the Friedel-Crafts catalyst forms a chloromethylene, which is linked to the styrene group. What we do is to replace this chlor atom with a functional group which is positively charged. And normally it is amines, it could be a tertiary one, as a T3-melatin, as this the case is, with a quaternary ammonium ion, or it can be here the union of a tertiary ammonium cation, or here with another reactive agent with methylamine. We also have a quaternary element with a different oxydrylic group, which conveys different features. And indeed, we can do the same with these reactive agent too. And we introduce another aminic tertiary group with different features when compared to what we see there, because in that case the aminic groups that are introduced can also act and serve as loci for hydrogen bridge loci.